I'm very happy to be here, and I want also to say hi to everyone which is behind the screen. Thank you also to you for choosing to attend this talk. So as you said, this is a talk about isogeny-based cryptography, and I'll start by giving you the main goal of this talk. So first of all, this is what I'm going to tell you is strictly contained in this paper in collaboration with Laia Amorós, Christine Lothar, Chloe Martindale, and Jana Sotakova. And the goal of our paper, which is also the goal of this talk, is to review the connections between these three apparently different worlds, the worlds of supersingular isogeny graph, quaternion algebra, and Bruhat Tits trees. So you have to know that supersingular isogeny graphs are very often looked from the perspective of quaternion algebra for what is called during correspondence. Unfortunately, I will not have time to recall this correspondence here today, but what I want to do is to highlight the connections with this object, mathematical object, that you will find less often in the context of isogeny-based cryptography, and to, in some sense, suggest maybe in the future Bruhat trees as a practical tool to use in cryptanalysis of isogeny-based cryptosystem based on supersingular isogeny graph. So this is not the first time that Bruhat trees appear in the context of isogeny-based cryptography. Here I just put a couple of other references in case you're interested. So let me start by putting a little bit of context here. So our main characters will be supersingular isogeny graph, which were first considered by Mestre and Osterley in the 80s, but we have to wait until 2006 before they were brought into cryptography by Charles, Gore, and Lothar, who proposed supersingular isogeny graph in the context of a hash function called CGL hash function, and which is based on random walks of supersingular isogeny graph. And later in 2011, Zhao and DeFeo proposed the supersingular isogeny graph for a Diffie-Hellman key exchange, and based on this proposal, there was a submission to the NIST competition called SIKE for supersingular key encapsulation. And this submission has been named a third round alternate candidate in July 2020, and now the community is asking for a deeper study of its security. But what is a supersingular isogeny graph? We had already a nice introduction. I'm going to repeat something you already heard. So in order to define them, we need to fix two primes, P and L. P in context of application is going to be very large, more than 400 bits, while L is going to be very small. I'm thinking really to L equal 2 or 3. And in order to define the supersingular isogeny graph over FP bar, I'm going to define the set of vertices and the set of edges. Our vertices will be isomorphism classes of supersingular elliptic curve defined over FP bar. And what is nice about supersingular elliptic curves is that I can label each one of these class by an element in FP square, and by associating to each class the corresponding J invariant. So this implies in particular that any supersingular isogeny graph is finite in terms of vertices. And our edges will be isogenies. An isogeny is a non-constant rational map between two elliptic curves, which is also a group homomorphism. And we're going to restrict our attention to isogenies of degree L, which we consider up to a certain equivalence. So here an example for L equal to and P equal to 127. So just to show you that here everything is very explicit, let's have a look to one of these edges. For instance, this one. So 201 and 132 are the J invariants of two elliptic curves that I can write in their corresponding short bias transform. And our edge is an isogeny, so that I can really write down explicitly as a rational map, and this is an isogeny of degree 2. As we saw in the previous talk, an important property of this supersingular isogeny graph is the fact that if we make some exception, and if you count the number of outgoing edges from each vertex, this number in this case is 3, which is 2 plus 1, and in general, a supersingular isogeny graph will be L plus 1 regular. So how they are used in the context of applications, for instance, in SIKE, the main idea is that Alice or Bob, she starts from a given vertex, which will be a public parameter, and she performs a random walk. This random walk is her private key. And the endpoint of this walk will be her public key. So if we look from the point of view of an adversary, the adversary will be the starting point and the ending point of this walk, and their goal is to recover a path between these two vertices. Or, since a path is a composition of isogenies, the adversary has to solve what is called the isogeny finding problem. So given two supersingular elliptic curves, compute an isogeny between them. And cryptosystems, which are in the context of, isogeny-based cryptosystems, are basically based their security on the hardness of this problem. And here, when we work with supersingular isogeny graph, if we want to study the security, the difficulty of this problem, we need to collect information on their structure. And maybe we can do that by a different point of view. Okay, so since everything is based on walks, on this supersingular isogeny graph, let's have a look to walks, in particular to non-backtracking walks. So walks for which I do not stop and go back. These are the kind of walks that we have in SIKE and the CGL hash function. So let's consider the set of non-backtracking walks of a given length n from a given elliptic curve in the supersingular isogeny graph. This set is in one-to-one correspondence with cyclic isogenies of degree L to the n from E to another curve E prime. And in its turn, this set is in one-to-one correspondence with cyclic subgroups of order L to the n in the L to the n torsion subgroup. So basically, for studying the walks, we can study these subgroups. But we know very well the structure of the L to the n torsion subgroup. This is a direct product of two cyclic groups of order L to the n. So I can write down the two generators, let's say Pn and Qn. And now if I take a cyclic subgroup of order L to the n here inside, well, I can write the generators of all these possible subgroups in terms of Pn and Qn. And this allows us also to count the total number of cyclic subgroups over equivalently the total number of non-backtracking walks from a given curve. Let's get even closer to one of these walks. So remember the notation, Pn and Qn is a basis of this L to the n torsion subgroup. This basis also allows us to fix a basis of the L to the I torsion subgroup for every I from 1 to n minus 1. And now if we take a subgroup of this kind, for instance, generated by the point Pn plus AQn, this is the kind of subgroup that appears in SIKE. Well, we can consider the corresponding isogeny. Just we consider the isogeny in that sense E in the elliptic curve obtained by quotienting E by this subgroup, and we can consider the corresponding walk. And what is nice is that the elliptic representation of this coefficient A, because we can write A as sum of AI L to the I, can be used in some sense for reconstruct each step of the walk. So imagine that here we want to go from E to this quotient of E, and at every step we are going to work in a higher power of the L torsion subgroup. For instance, in the first step, we are working in the L torsion subgroup, and here we are defining basically a subgroup of order L of this L torsion subgroup, and the coefficient A0 allows us to identify exactly which one. In the next step, we are going to use A0 and A1 in order to get the subgroup of order S square in the L square torsion subgroup, and so on. So each one of these AI can be seen as a direction that I take at each step of my walk. So I'm going to just switch a little bit translate this in another form. So instead, we're going to work with matrices. So imagine here I am at the 0 level. So I'm working here in the L to the 0 torsion subgroup. There is just the identity, so just one subgroup of order 1. And at the next step, each one of these matrices represent a subgroup of order L in the L torsion subgroup. The corresponding form can be found by multiplying on the left by P1, Q1, the basis of the L torsion subgroup, and so on. So then I will be in the L square torsion subgroup, and again, each one of the matrices can be seen as the generator of the cyclic subgroup of order S square, and so on. And this process can be bring to infinity by working instead of a basis of the L to the n torsion subgroup with what is called the Tate module. Tate module for an elliptic curve is the cross product of ZL cross ZL. I can find a basis, PQ, and this basis contains information of basis of every power of the L torsion subgroup. So basically for L equal 3, so this was just an example, I get this infinite tree. And as I said, at each step, I have a notion of directions. So we can interpret every walk from the identity matrix, every level increasing work from the identity matrix towards the infinity, let's say, as a non-backtracking walk from a given elliptic curve in the supersingular isogeny graph. And so we get a kind of structure. But what is interesting is that this object is actually has been studied in itself, and this is a Bruhat trees for L equal 3. So I'm just going to recall what is actually the classical definition for Bruhat trees. So here we work with the notation N instead of P, which is more classical, just to match the notation which comes from a supersingular isogeny graph. And so every vertex of these Bruhat trees can be defined from different perspectives. So the perspective that we've just seen in the example is every vertex is a class of matrices in this quotient of a group of matrices. But we can also define vertices either as classes of homothetic ZL lattice in QL², either as maximal orders in the quaternion algebra M2QL. The most classical way to define that you will find in the literature is the first one. So let's start from there. What is a lattice in QL² is just a ZL module of rank 2 of QL. This can be written by fixing a base UV and writing every element as a combination, linear combination of U and V with a coefficient in ZL. On this set of lattice, we put an equivalence relation, which is two lattices are homothetic if and only if there exists a non-zero element in QL such that L1 is equal lambda times L2, and these homothetic classes will be the vertices of our tree. So now we have to say when do we put an edge between two such vertices, and so we get to the notion of adjacency. So L1 and L2, two homothetic classes are adjacent if we can choose the corresponding representative L1 and L2 in a way that they verify this condition. And I want just to highlight that if L1 and L2 satisfy this condition, in particular L2 is a cyclic sublattice of index L of L1. Just as an example, if I have U and V, the lattice generated by U and V, then there exist L+1 sublattices that verify this, and they can be written down by multiplying on the right by these L+1 matrices. So Bruhat trees are the graph for which vertices are homothetic classes of lattices of QL², and edges pairs of adjacent homothetic classes, and it's been shown that this is a L+1 regular infinite tree. So now I said that there are other two descriptions, how we go from one to another one. Well, if we want to move from lattices to matrices, well, if I have a lattice generated by U and V, these U and V are vector in QL². So by putting them in column, I will get a matrix 2 by 2. But I have, for getting a one-to-one correspondence here, I have to quotient by this group of matrices that just acts as a change of basis. Instead, if we want to move from the representation from lattices to maximal orders, we basically associate to every homothetic class of lattices the corresponding endomorphism ring, and this is a maximal order in this algebra M2QL, and vice versa, every maximal order in M2QL is the endomorphism ring of homothetic classes. So if we go back at this point to the first slide, where we wanted to highlight this connection between these three apparently different words, what we've seen also is that this Bruhat tree can be in some sense split in three equivalent in three different forms. One in which vertices are the lattices, another one in which are matrices, another in which we are maximal orders. And I do this just to highlight the connection between both supersingular isogeny graph and quaternion algebra. For instance, on the left side, if what is the connection between supersingular isogeny graph and Bruhat trees? The idea is that if I have an isogeny between two elliptic curves, this induces a ZL linear map between the corresponding Tate module. So now what was an edge between two elliptic curves becomes an edge between two ZL lattice in QR square. On the other side, when I work with maximal order in a quaternion, in this specific quaternion algebra, if I tensor with respect to ZL, I get a maximal order in the quaternion algebra M2QL. So this is a way for moving from quaternion algebra to Bruhat trees. And remember that one of the main problem in isogeny-based cryptography is also to make this Dering correspondence explicit. This can also be this problem is also called enormous swing ring computation. So we hope that this Bruhat trees, and in particular its description as vertices of matrices 2 by 2, which is also the same description for, so also edges are matrices 2 by 2. So this easier representation can help us either in getting some nice properties of the supersingular isogeny graph, so some information about the structure of supersingular isogeny graph, or since in some sense moving in supersingular isogeny graph and moving in the context of quaternion algebra corresponds also to walks in these Bruhat trees, maybe that can help in establishing more explicit, helping find, get, in some sense, how to say, to make this Dering correspondence more explicit. So I end here, and I thank you very much for the attention.